just barely taught at the top. Hopefully this concept will be well taught. Okay. So, but at the top it'll be just barely taught. There'll be zero tension in the cable if I'm going exactly at that speed. And then at the bottom, if the speed stays the same, will it stay the same? No, it's actually going to speed up on the way down. So these problems actually are somewhat complex. It would take a lot of skill to keep this the same speed all the way around. So we would actually have to use something from chapter 6 to figure out the speed at the bottom, conservation of energy. Okay? But yeah, if we kept it the same speed, at the top we'd feel 0 Gs. At the bottom we'd feel, well, 1 G plus 1, right? We'd feel 2 Gs at the bottom. Okay? Okay, so let's do another example of one of those. Okay, yes, we've got this. We are good. Okay, so here's an example of a problem that we can do with just G-force. Law. All right, a rider moving in a 3.75 meter radius circle feels 1.2 Gs at the top of the circle. Here, let's draw a medium-sized circle. That's a pretty good circle. I know, aren't I amazing? Oh yeah, the perfect circle, a professional. They used a roll of masking tape to do that, actually. You know? Yeah. How do you do that with like a bamboo tablet? Do you make like a protractor for the little stylus? I don't know. Okay, so I'll have to figure that out, right? Okay, do you just use, I suppose I could just use a circle jig, right?
Oh,
you know?
I think that's
okay.
Like you put one and then you drag out the radius of what you want it to be.
For smart boards or something like that, yeah. Okay, so let's do this one. If I'm feeling 1.2 Gs, if that's what I'm feeling at the top, what is the ride really doing?
2 Gs.
It's really 1 G more, right? So it's going to actually be 2.2 Gs. So the ride is actually doing 2.2, and so at the top it's 2.2 minus 1.2, or I'm sorry, minus 1, right? Equals 1.2. Okay? And then at the bottom, what is it going to be? What are we going to feel? 3.2, right? At the bottom, we're going to feel 3.2 Gs. Okay? And this is, by the way, what the Roundup does. They've now renamed it the Eruption at Oaks Park, right? They spin you up. The ride pulls about 2 Gs, which isn't that pleasant because most of you are tall enough that your head no longer rests on that like padded mat. And you're sitting there like this, and then they tip it up on end, and you feel about 3 Gs at the bottom, about 1 G at the top, 3 Gs at the bottom, 1 G at the top. And then it runs for like 14.79 minutes or something like that, right? It just goes on and on and on. You're like, you know? So it's fun to begin with. Near the end, it's not as fun, right? Be sure to get a lot of good, careful data on that one. Now, the final thing says, what is their tangential velocity? Should we use what we feel the ride is doing, or should we do what the ride is really doing? What it's really doing, okay? So this is in Gs, right? This is Gs of acceleration. So 2.2 Gs times 9.81 is right? And then we want, can we not talk? Can we have a YouTube video where I'm not saying, can we not talk? Okay, so, and now we want to find the tangential velocity. I'm going to use this thing. Obviously, if I solve for V, V is the square root of AR, right? And so the square root of 21.582. And then the radius is 3.75. So that times 3.75 raised to the 0.5 power. And I get 8.996 meters per second, right? And then the only moral dilemma about this problem is how do you round that to 2 sig figs? I think it's 9.0. Yeah? That's not so hard. Is that hard?